and I can see there like Chad is here and Catherine is here. So, okay, guys, you go ahead and ask questions. So is it the dark matter worksheet? Do you want to start with that?
Sure.
Okay, so I'll open this thing. Let's see. And I think the Hubble's law was harder worksheet than this, but this is also hard because, well, does this open?
I kind of felt like I was repeating myself a lot on this one. That's the only thing.
Were you able to open this? Let's see. Maybe I need to click over here. And then click on this maybe. Okay, okay, good. So here it is. So who wants to start? Maybe you can start and then like, you know, we can answer. Mary, you want to do it? You want to start?
Yeah, sure.
Yeah, Chad was the only one last time.
Yeah, I'll take over this time.
Okay, good.
So for number one, it's saying where is the vast majority of mass in the solar system located? What object or objects account for most of this mass? And I answered that the majority of the mass is located at the center with the sun.
Yeah, exactly. And then if you actually, like, what would you say then? The rest of the planets, basically, how much do they contribute in terms of percentage?
Like probably, yeah, like less than 1%.
Yes, very good. Because, right, when you take the one means 100%. So this would be like, you know, 10th of percents, and this is hundreds. So you can see even when you come all like, you know, up to the end, not even like 1%. So it's less than 1%. And that's exactly what you know from before, right? That 99.99% of the mass is inside of the sun. Okay, very good. Then which student is correct, number 1 or 2?
I said student number 2.
Yeah.
Is that a little wrong? Is that wrong?
Yeah, no, it's perfectly correct, right? So most, like 99.99% is in the sun. And then, yes, surely you add a little bit of the mass, but it's really tiny fraction, right? So even like all of those planets don't add up even to 1%. Okay, very good. Number 3?
They get slower as you move away from the sun. That's how I answered that one.
Very good. And you can see that Mercury moves fastest, and then as you're moving further out, they all slow down. Okay, very good. And then here they tell you why this is important, right? Because this is really important paragraph, this one over here. So let's read this like out loud and then answer this as we go.
A planet's orbital speed depends on the gravitational force it feels. The strength of the gravitational force depends on the amount of mass that is inside the planet's orbit, as well as how far away the planet is from this interior mass.
Very good. So this is really important. The speed is a good indicator of the gravitational force. And that is like universally applicable. When you look around like supermassive black holes, the stars move like really fast because they feel a lot of gravity. So the speed can always is related basically to the amount of the gravity that something feels, and gravity depends, we know that, on the amount of the mass and how far you are from the other mass. Okay, and so then how do we connect this to the next question?
Yeah, sorry, I wrote in gibberish here, it seems like. One closer to the sun. Okay, I'll probably just not read my writing. Pretty much that if it's closer to the sun, it experiences a higher gravitational force rather than one that's farther away. It'll experience less gravitational force.
And the reason for that now, if you want to think just like a little bit more, is basically most of the mass is inside of the sun. So these masses of the planets, they will be really small, regardless if you're talking about Mercury or you're talking about Jupiter. But what for certainly is like changing is the distance, right? Jupiter is like 5 times as far from the sun than the Earth, right? So the gravitational force for that reason will be 25 times weaker, right? So the further out the planets are, the less gravitational force they will feel, and that is confirmed by the speeds that we observe. The speeds are less and less and less as we see in that table. Okay, Catherine, if you're here, do you want to try to fill in the blanks?
Sure. There are 7 planets inside Neptune's orbit and 0 planets inside Mercury's orbit.
Mm-hmm.
However, the interior mass for Neptune is approximately the same as the interior mass of Mercury. Neptune is much farther from the sun than Mercury. Therefore, the gravitational force exerted on Neptune is weaker than the force exerted on Mercury. As a result, Neptune has an orbital speed that is much slower than the orbital speed of Mercury.
Very good. Perfect. And now the hard question. Question 6 is hard. So what do you say about question 6?
I put that if there was the addition of a very, very large amount of mass, that the interior mass of Saturn, Uranus, and Neptune would increase, which would also increase their gravitational force and their orbital speed, and that it wouldn't have any effect then on Jupiter backwards towards the sun.
Perfect, perfect. You said it exactly how I would say it. So for Jupiter, it would not change the interior mass because it's outside of its orbit. But for the other planets that you said, for them, it would make a difference. They would feel more gravitational force. As a result, they would move faster. Perfect. That's it. Great. Part 2. Mary, you want to go back to you?
Sure. So let's see. One way to estimate the amount of mass, or do you want me to just answer number 7?
No, you can read.
Oh, okay. One way to estimate the amount of mass in a spiral galaxy is by looking at how much light the galaxy gives off. Where there is more light, there must be more stars and hence more mass. When astronomers measure the amount of light coming from the different parts of the galaxy, they find that stars are very concentrated at the central bulge of the galaxy and very spread out as you look outward through the disk.
Very good. And so thinking about something that is close to us, like the Milky Way galaxy, that's exactly what is happening, right? Inside of the central region, like the bulge region, the density of the stars is like, so high that if the sun was there, the night would never come. And definitely there is no way you can have life over there just because it would be like, so hot. So we know there is like a high density of stars over here. There is more luminosity, more light coming from this region. As you're looking through in the outskirts of the galaxy, going through the disk, there is less and less stars and they're less and less luminous, and basically that's what we see. And we think most of the mass of the galaxy, as we look at it, is like in the center of the galaxy, and then there is less and less stuff outwards. Kind of a very similar to the solar system, right? Just on a larger scope. So that's basically what you get from the picture of a galaxy. Okay, so then question 7.
Based on the information, we would expect that at the center, the stars would be orbiting the center faster than the stars that are farther out, based on that information.
Yes, but the question is, where would you expect most of the mass?
Oh, oops, sorry. It would be at the bulge of the galaxy. Sorry.
Exactly. So most of the mass you would think like within this first circle, right? Because this is kind of where the bulge is. Okay, very good. So then how about question 8?
The way that I would rank it, being the strongest to the least, it would be star A, and then the sun, and then star B.
Very good. Why? Again, because most of the mass is here, and so you're not adding much mass as you move over here, but you're certainly increasing the distance, so the gravitational force would be less and the speeds of the stars would be less. Okay, very good. And so then which graph would match that?
Curve number 1.
Okay, very good. And so this is now that rotational curve. This was mentioned in the chapter with the Milky Way galaxy, but not really in some extensive details. But now in this last chapter, we are talking more about these rotation curves. And they simply, this is the center of the galaxy over here, right? They relate the distance away from the center to the speed of the stars or gas or whatever you're observing in the galaxy. And so this is what we would expect. Further out from the center, things should slow down. This is exactly the same graph as the speeds of the planets in the solar system, right? If the sun is here and this is looking further out from the sun, the speeds of the planets would decrease. Does that make sense?
Yes.
Okay, very good. Now question 9. Oh, that's what we said, right? Curve 1. Okay, now question 10.
So the way I drew it was that star A was right where the arrow is.
Yes,
and then
excellent.
About halfway between the end of it and star A, I put the sun, and then star B at the very end.
Exactly, something like this, right, for the 3 dots.
Yeah.
Okay, very great. Okay, so I'll clear all. Fine, perfect. And then, okay, so now you want to take Chad? You want to say something?
Sure.
Okay.
Describe how the star's orbital speed shown in the real rotation curve for the MWG are different from the orbital speed shown in the rotation curve you chose in question 9. Question 9, it's dropping off. Actually, what is that called? The distance square law.
Yes,
It
it is.
off by
Very good.
distance
Hmm.
squared. And the other one, it increases to a plateau and stays right after a central bulge.
Yes, very good. And so basically for those three stars that we are observing, one being here at the central bulge, all of those speeds were basically the same, right?
Same.
On this plateau,
Yes.
as you said. And here that would not be the case. They would decrease, as you said, as the inverse square relationship. Okay, very good. Number 12.
Using the real rotation curve NWG, provide a new ranking for the orbital speeds of stars A, B, and the Sun from fastest to slowest. Describe the difference between these rankings and the one you provided in question 8. A, B, and B and the Sun are all orbiting at the same speed. That means that they've all increased. Star A, Star B, and the Sun have all increased in speeds.
Compared to what?
Most.
Very good. So they have higher speeds, basically, than what we expected, right? Based on the picture of the galaxy.
Yes, a lot higher.
Yes, very good. So then what does that imply for the question 13?
Based on your answer in question 12, would you say that most of the mass of the Milky Way galaxy is located at the center, as in the case of with our solar system? Explain your answer and reasoning. Most of the mass is not located in the center. It has to be evenly distributed in between each of the locations which the stars were located at. And it has to be evenly distributed in between those and probably even more on the outside edge.
Yes, very good. So how I would say that, it's just like the mass doesn't appear to be located at the center, right? Because we can see that there is like more gravity that stars are feeling, that's what we would expect, and that's reflected in the higher speed. So the mass is not most of it is not in the center, but there is more mass beyond that bulge, right? Than what we expected. Okay, very good. Question 14.
Based on NWG's real rotation curve, and your answer in question 11 through 13 is gravitational force felt on NWG's stars greater than, less than, or about the same as what you'd expect from question 8 and 9. Each one of the stars A through B, or through Sun and B, all experience more gravitational force on them because they have more velocity. And star C or star B has the greatest increase in that force.
Very good. Excellent. Excellent. Okay, Catherine, you want to go back to students 1 and 2? Which one is correct?
Sure. It is the first student that is correct in their statement that the real rotation curve of the Milky Way galaxy indicates that there is more mass throughout the outer regions of the galaxy. This increase in interior mass for the three stars increases the gravitational force as it is directly proportional to mass. The second student is incorrect in their assessment, as they are indicating that the first rotation curve shown in question 9 is correct rather than the real rotation curve.
Okay, very good. The student 2, I think, says something. So since the stars are all going by the same speed, where the mass is located must not affect their speed. So I think that's where this is where the light goes, right? This does not sound okay. So this is the biggest mistake because it does, right? The speed depends on the gravitational force, and gravitational force does depend on how the mass is distributed, right? Or where
as long
it's
as we trust Newton's laws.
Exactly. Okay, very good. So student 1 is completely correct. And then this is just like a summary. So Marie, go back to you. 16.
So let's see. Astronomers initially thought there was more mass in the center of the galaxy than in the rest of the galaxy because there's more light coming from the center. Describe how astronomers' observations show these initial ideas are wrong. And it's because if you move out towards even where it is vast, it's not so dense throughout the solar system. The stars are still moving at like a constant rate.
Chad, what did you say there?
16. Let me get to it, actually. Astronomers have been able to find orbital speeds for stars that are very close to the center and that are at the far reaches of the Milky Way galaxy. All the evidence combined shows that the mass center model is false.
Okay, good. And Catherine, what did you say?
I put that further observations of the orbital speeds of stars not located within the central bulge The original region, thought to contain the majority of the mass due to its concentration of light, have shown that the majority of the mass is not actually in the center of the galaxy. Orbital speeds have been shown to actually increase before plateauing out the farther the object is from the center of the galaxy. If the initial thought had been true that most of the mass of the galaxy lies within the central bulge, then the first rotation curve from question 9 would have been true, whereby the greater the distance from the central bulge, the slower the orbital speed. The observations that have resulted in the real rotation curve for the Milky Way galaxy debunks the initial thought that most of the mass in the galaxy, according to the concentration of light, is within the center of the galaxy.
Okay, very good. And actually, through this question, you can see kind of the evolution of the science, right? Because initially, the only tool we had was like, photographic plate. So we would take like a photo of the galaxy, and we would think, okay, most light comes from the center. That's all of the stars are, or most of the stars are, most of the masses. And then we made spectrometers. Spectrometers are put on the telescopes. They can break light into different wavelengths, and then you can study actually, what is happening over there and how the study the speed of the stars, right, by the amount of the Doppler shift. Yeah. And then we build better and better so that you can really resolve throughout the disk what is happening. And that's how we then learned that then basically what we see was not really what is happening over here, because the development in technology gave us completely different picture. Okay, very good. And then question 17.
Is this still for me? I'm sorry.
Yeah, whatever.
Okay, sorry. Yeah, I'm sorry. I haven't really gotten like really great answers for these yet. I just kind of made quick notes, but pretty much it's I said that there's let's see, is there more or less mass in the Milky Way's disk and halo than we can see? I would say that yes, because dark matter is perturbing gravitational influence and
yeah. So way more mass. Why? Because we can see that those orbital speeds indicate that there is way more gravity in the galaxy. The reason for that is like, you can think about, let's say, Earth, and the Earth has like specific speed as it orbits the sun that matches the gravitational force that it feels. But what would happen if you give the Earth like, 5 times higher speed? What do you think would happen?
Like if the Earth is moving at is moving 5 times faster?
Yeah, somebody comes and pushes the Earth and gives it now 5 times more speed than what it has now.
And it's not because the mass in the center is increased, right?
Just like some magic, like some, I don't know, superhero, superpowers.
I think then, wouldn't it just continue in the direction that it was pushed then? If it was
exactly.
Velocity, wouldn't we?
Yeah. So then exactly. The sun would not be able to hold on to the Earth, right? The Earth would leave the solar system, let's say, like to put it in simple terms. So the same thing, the fact that these stars are moving so fast and the fact that they're bound to the galaxy tells you, right, that there is way more gravity to hold those stars, because they're not flying out of the galaxy, but they're held inside of the galaxy, and they go around the galaxy in these like circular orbits or whatever. And that tells you that there is more gravity than what we perceive by looking at the galaxy. So that tells us that there is way more mass in the Milky Way's disk than what we see, right?
Right.
Okay, very good. Because I personally think that dark matter is really like easy for students to understand, just because we can use this analogy to the solar system. And it's really I think it's powerful for you that you can understand that why we know that there is more mass in galaxy and then in the clusters of the galaxy and in the universe as a whole than what emits the light. And that is completely fine, because we know about particles that don't emit the light, right, but have mass. And so it just tells us, we need to find that particle, whatever makes the dark matter, right? We don't know what that is. That's a big question, but we know that it's out there. The challenge, again, just not to be really suspicious, is it really there, right? The challenge is all of our technology is kind of geared towards the same principle. We build the telescopes, we collect the light, we analyze the light. And from that light, we know everything about the chemical composition, the motion of the stuff, of the stars, of the matter, whatever. But the dark matter obviously does have a mass, but it does not interact with the light in a way that it does not absorb or emit the light. And so when we build telescopes and collect the light, we cannot find any information about the dark matter itself, right? So what we need to change is the approach, right? How we're gonna catch that dark matter particles. So some new technology. And I don't know what that is, okay? But it's something else, something that is not catching the photons, right? But it's catching something else.
Or creating it in some lab somewhere, somehow.
Yes, exactly.
Accelerator. Yeah.
Exactly, because we think like, because you read those, both chapter 17 and 18, whatever the dark matter particle is, based on the Big Bang model, it should have been created within those first like 5 minutes, right, of the evolution of the universe. So it's there, and it's have always been there. So it's now just the question, how do we find it? And many people make analogy between dark matter particle and neutrinos. The challenges are similar. We don't know how to catch the neutrinos, even though like, sun produces billions of them. But we cannot catch them because we don't have the technology. We only like indirectly have the evidence for neutrinos. Okay, so you did great on this one. Very proud of like all three of you.
Good.
Okay, any other questions from
Not really.
like, not really? So was this pretty simple week?
I think so.
It wasn't bad.
Yeah,
Okay,
for the most part, yeah.
I know like on campus, chapter 17 is really hard. Students get like overwhelmed with all of those like, eras of the like after the Big Bang. But I think mastering astronomy helps with that.
Mm-hmm. Yeah, it really did, especially with the ranking of them. It really solidified the order. So.
Okay, very good, very good. That's the new thing I put like this semester, and I really liked it. So I think I'm going to continue doing that even now in the fall.
Is this your first time using this textbook?
This textbook I've been using, but I kind of relied more on my own stuff. But I think the Mastering Astronomy, especially like for online environment, is really good because it may like, forces students to do things and to play with things, and rather than just like read the textbook. And I don't know, 3 of you were like really amazing this semester. So I'm really happy, like, how this worked out. So hopefully that will be the case next semester as well.
Well, thank you.
Thank you. You really make me happy.
It's a very enjoyable course. I'm really glad I took it.
Okay, really? Even online, it was quite good?
Yeah, I've always felt that
loss in person, but when you are online versus being in person, but I still enjoyed it. And then I travel and take it at the same time. So
very good, very good. I love it on campus because it's really nice, like, to discuss all of these things in the classroom and students ask questions. And it's always like, everybody's interested about these things. So it gets to be like engaging, like lecture class. But online, I'm trying to create the similar thing. So
yeah, because at least when you're in class, like if you have the immediate question, you can ask it right there and then.
Exactly.
Whereas online, by the time you get to the end of the chapter or the end of the lecture notes, you've already forgotten what that initial question was. So
yeah, exactly. Okay, so I posted today 2 quizzes, and I think they all have like, each has like 14 questions, and you have 14 minutes for each one to do. But and they should be pretty straightforward, I think.
They weren't bad.
What do you say?
I completed them earlier. They weren't bad.
Okay, good. Did you kill both of them?
Yeah.
14 points on each.
I think I lost 1 point.
Oh, okay, good. It's okay to lose 1 point.
Oh, last week I went and got D on one of your quizzes.
Oh, really?
Question. Yeah, I got stuck on a question and burned up all my time.
Oh, no.
That's okay, Chad. I'm quite sure you'll get like strong A.
Oh, I still have over 100%. So I'm
okay. Okay, and I'll try to catch up on grading like by Sunday or something so that I can post grades and you can all review and let me know if I missed anything.
Okay.
Oh, yeah, I was curious about that with the writing prompts and everything.
Yes, I'm taking the whole weekend for like reading all of this and then like grading.
Like for the grades of those. Yeah, no, I just wasn't sure because this is my first like online course, so I'm not sure how like the grading system really works on that stuff. So
yeah. This is my first time actually that I put a lot of writing. Before I had exams, but then I decided like I'll drop the exams, just have like quizzes and then like a lot of writing because it actually helps me out. I can see immediately who spends some time studying and who doesn't study like at all.
Are we doing a final exam for this class at all?
No, not at all. You're done. When you take your 2 quizzes, then you're just waiting for me to catch up with the grading and then get your grades.
Yay! Sorry, I'm so over finals right now. So
I can imagine. Okay, guys, so I'll send, if you don't have any other questions, then I'll make a few more announcements. Like I'll send you a list of lectures that we have going on for like, not just astronomy, but also like geology and the other like disciplines. And then if you have time, stop by. Usually they're really nice. We have like 100 people show up and they're open to public. So you can bring somebody if you want, and then stop by and introduce yourself. So I'd like to meet you.
Okay, that's the September 10th.
The first one will be September 10th, and then we go from then on. I think there will be another one the same week on Thursday, and then there will be professor from San Diego State, November 8th. He's going to talk about supernovae and the dying stars, and he's pretty awesome. I know him since I was like a grad student. He was a postdoc at that time. And then there will be professor from City College, Lisa Will. She will be talking about something as well. So we'll have like a lot of different.
Okay.
Yeah.
I was going to say Neil deGrasse Tyson is also here in September.
Oh, really? How do I get him to come to Mesa?
He's going to be at, I believe it's the Civic Center the last Wednesday, I think, of the month, the 26th, maybe.
Okay. And is he doing something like presentation, some kind of a...
Yeah, he's doing a lecture at the Civic Center.
At the Civics, okay. I'm quite sure we won't be able to get him to come to Mesa.
Probably not, but if you wanted to go.
Yeah, maybe I can do that and take my kids as well. Okay, thank you for letting me know.
I think it was 200 if you actually wanted to meet him.
Oh, really? I can meet. Okay, I've seen him at one conference. I never spoke to him, but I did see him. Like,
does he sign T-shirts too?
I don't know.
Who knows?
Okay,
I just know he's the night before Beyonce and Jay-Z.
Oh gosh.
Then I'll just camp over there, okay? Okay, good. Okay, well, anything else?
I don't think so.
Okay. Good. Well, I'm really thankful that you were joining these Zoom meetings. So thank you for that. And we always had like great conversations. So I hope to see you on campus at some point.
For sure.
Yes.
I'd like to come to the stargazing.
Yes, please. The sky is so beautiful right now. Like every single night I go, like spend like 5-10 minutes just like looking at the planets. And they say like Mars won't be like this bright until like 2030 or something like that. It's the closest to the Earth now than it will be in the next 12 years or something. So it's super bright.
Yeah, it really is.
Yeah. Okay, great. Okay, so then see you then September 10th, Monday.
Sounds good.
Okay, good luck with finals, and then I'll see you.
Thank you.
Thank you.
Thank you. Bye-bye.
Bye.
Bye.